Hello everybody, welcome back to my channel where we solve rather difficult integrals. And today's integral is a very nice log-trig integral that can be solved using different methods. And we're going to see two of them. Today, the first one being the fastest one, and a second one which needs much more time but is a very nice development using the series expansion of the beta function. So here we go for the first calculation of this integral. The easiest method is to first let sine squared theta being equal to x, then sine theta equals square root x, and if you differentiate both sides, you get cosine theta d theta equals dx by twice square root x. Here you recognize 1 by tangent theta, which is 1 by sine times cosine. So here you have cosine theta, which is the x by 2 square root x, and you're left with 1 by sine squared, which is 1 by square root x. So our integral I equals the integral from 0 to 1 of log sine theta, which is square root x, log cosine theta, which is square root 1 minus x, divided by square root x times dx by 2 square root x. You have here simplification. You have 1 by 2 here, square root here, and all this into logarithms. So you have some factor 1/8 here, and this 1 by square root x, 1 by square root x cancels out pretty nicely. So you have I being equal to 1/8 of the integral from 0 to 1 of log x, log 1 minus x, divided by x dx. So now is the time for an IBP. We have to use the polylogarithms defined this way. Polylog n of x equals the sum for k starting at 1 of x to the kth power divided by k to the nth power. These functions have very nice properties, like for example len of x of 0 equals 0, len of 1 equals zeta n, with zeta the Riemann zeta function, and polylog n plus 1 x equals the integral, well, the entire derivative of polylog n of x divided by x dx. We then use a particular formula, which is that polylog 1 of x equals negative log 1 minus x, and here we can use this formula for our IBP. Let this here being equal to v dot, and here this log x being equal to u, and you have I being equal to 1/8 of uv, while v dot equals negative polylog 1 of x. You have v equals negative polylog 2 of x. So this function polylog 2 is named the diagram. So you have negative diagram of x times u, which is log x, taken between 0 and 1, and you have then plus 1/8 of the integral from 0 to 1 of dialog x divided by x dx. Thanks to this development, we know that polylog of x is equivalent to x when x is near to 0. So we know that this function into brackets goes to 0, because in 1 this is defined and this goes to 0, and in 0 this goes to infinity, but this goes to 0 with the same speed as x, which is much faster than log x goes to infinity. So this totally cancels out, and we're left with 1/8, the integral of dialog x by x, which is, thanks to this property, equal to 1/8 trilogarithm of 1, which is theta 3, minus trilogarithm of 0, which is 0. So 1/8 zeta 3, which is here zeta 3, the Paris constant. Alright, now we know the value of our integral, 1/8 Paris constant, and we're going to calculate it in a second time using the beta function. So we know that the beta function is defined this way. Beta AB is a symmetric function. You can switch up A and B. And it is defined as twice the integral from 0 to pi by 2 of cosine 2a minus 1 theta, sine 2b minus 1 theta, d theta. This function is defined as gamma function with this formula: beta a b equals gamma a gamma b divided by gamma a plus b. And while the gamma function can be differentiated twice, the beta function can be differentiated twice as well. So you can define beta 1 0, beta 0 1, and beta 1 1, which will be very useful because we want here to apply Leibniz rule, which is switching up the differentiation and integration operators, and we can, because the beta function is can be differentiated and the function here is always continuous. So we let beta 1 0 being the derivative for the a variable. So beta 1 0 of ab equals twice the integral from 0 to pi by 2 of del by del a cosine 2a minus 1 theta, sine 2b minus 1 theta, d theta. Here we have to differentiate cosine theta to the 2a minus 1. A is the variable, and you have here the twice, which is important for the chain rule. So when you differentiate, you get cosine theta to the 2a minus 1, and you have twice log cosine theta. So beta 1 0 ab equals 4 times the integral of from 0 to pi by 2 of log cosine theta, cosine 2a minus 1 theta, sine 2b minus 1 theta, d theta. By the same development, we can prove that beta 1 1 of AB equals 8 times the integral from 0 to pi by 2 of log cosine theta, log sine theta, and shit, don't have enough space, times cosine 2a minus 1 theta, sine 2b minus 1 theta, d theta. So now we have to identify the a and the b variable in order to get some link between our integral I and the beta function. So we already have log sine theta and log cosine theta. So we have to identify cosine and sine. So here you have 1 by tangent theta, which is cosine divided by sine. So you know here the power equals 1, so 2a minus 1 equals 1, and here the power equals negative 1, so 2b minus 1 equals negative 1. This proves that a equals 1, b equals 0. In fact, the beta function is only defined for a and b greater than 0, or else the integral representations do not converge. So you have to let a and b be greater than 0, but if you differentiate the beta function, then you can use the limiting case for a or b going to 0 by positive values. So you can say that beta 11 of 0, 0 is the limiting case of beta 11 of a when a goes to 0 plus. So here we have the factor 1/8 and we want to do a limiting case, so we create a new value, which is a new function, which is, for example, f of here the variable we want that goes to 0, so b goes to 0 plus f of b equals 1/8 because we only want the interval here. 1/8 of beta 11 here. You let already a being equal to 1, and you have the b you're going to make converge to 0 plus. So now we have to calculate this value using the gamma form of the beta function. So we have to differentiate the beta function using two rules. First of all, gamma dot of x equals gamma x di gamma x. Second of all, di gamma x dot equals tri gamma x. And here we go. First we differentiate with the, let's say, the first variable. So we have beta 1, 0 of a, b being equal to, here gamma b is a constant, so we have gamma a by gamma a plus b. So you have gamma b treated as a constant, gamma a dot, so gamma dot a times gamma a plus b minus gamma dot a plus b, thanks to the quotient rule, and divided by gamma squared a plus b. Using this development, you can simplify very well with gamma b, gamma a plus b times, this looks like in AC, so here you have di gamma a minus di gamma a plus b, and all divided by gamma squared a plus b. Here you have consolations, and you're left with gamma b, gamma a by gamma a plus b, which is the beta function, and here di gamma a minus di gamma a plus b. While the function is symmetrical, when you differentiate again with respect to b this time, you're going to get this differentiated with respect to b, which is the same thing as this, but if you switch up a and b, so when you differentiate again, you get beta 1, 1 of ab equals this derivative, which is beta ab times, here you switch up a and b, so digamma b minus digamma a plus b times digamma a minus digamma a plus b minus beta a plus b times this times trigamma of a plus b, so you can just factor out with beta ab, and you get here negative trigamma a plus b. So now begins the fun part. You let first a being equal to 1, and then you try to use some limited developments of the f function. So f of b equals 1/8 of this, for a being equal to 1. So you have beta 1b divided by 8, and well, remember, we need I equals limit for b goes to 0 plus of f of b. So f of b equals beta 1b by 8 times digamma b minus digamma 1 plus b times digamma 1 minus digamma 1 plus b minus trigamma 1 plus b. And you can differentiate the digamma function and the trigamma function when, well, at 1 plus b when b goes to 0. So we use the Taylor expansion, and well, we need to remember that we want some limiting case, which is a finite interval, because if you look at our first interval, you have some inherent here, and 0, this goes to 0, because here we have log of theta divided by theta, and here you have log 1 minus theta squared by 2, so this goes to theta squared by 2, well, with a negative sign, but doesn't change anything. And here you have divided by theta, so this goes to theta times log theta, which goes to 0 in 0, and in pi by 2, this goes to infinity. This goes to infinity as well, but this is with a log speed, so much lower than tangent theta. And you have here log sine theta, which goes to 0, so in pi by 2, this function goes to 0, as well as in 0, and the function is continuous, which means all the function can be is bounded. You have a function that looks like this. Okay, here you have 0, here you have pi by 2, and you get something like this. Okay, and you see that this interval is finite because it's always greater than 0, except the bounds, and well, the function is finite, so the interval has to be finite as well. So 0 is smaller than I, smaller than infinity. So here, if you want to do some limited development, you have to know at which point you want to get. So here we can simplify this beta 1b using this formula. if you let beta 1 b, if you have beta 1b, you have here gamma 1, which is equal to 1, and here gamma 1 plus b, which is, thanks to the gamma formula, equals to b times gamma b. So here gamma b's cancel out and you're left with 1 by b. So this is 1 by 8b. Here you use z gamma z equals gamma 1 plus z. You take the log and you differentiate and you prove that digamma 1 plus b equals digamma b plus 1 by b. Okay, and here you have digamma 1 plus b minus digamma 1 with a negative sign. So if you simplify a bit here, you have 1 by 8b times, okay, here we just reverse this and this and this and this, so we get 1 by b digamma 1 plus b minus digamma 1, which is digamma dot 1 times b plus digamma double dot of 1 times of 1, not of b. Digamma dot of 1 times b squared plus little o of b squared. We can stop here because we want some finite results, and we know that this little o of b squared, which will cancel out with this 1 by b and 1 by b again, so this goes to 0 at the end, and this goes to infinity, but don't worry because we have this which goes as well to infinity, and we have this which should converge to our integral, to the result we're looking for. So this is the right development. You have to develop the digamma function to the second order because we want this little o of b squared to cancel out with 1 by b, 1 by b. And here you have minus trigamma 1 plus b. And while this is not multiplied by 1 by b here, only this one, you have to develop this to the first order. So you have this equals trigamma 1 minus trigamma dot 1 times b plus little o of b. Alright, okay, so digamma dot is just trigamma. So here you have trigamma of, well, okay, let's just replace everything. You have 1 by 8b times, okay, here you have trigamma 1 plus, here, well, let's say quadrigamma, even though the name isn't canonical. So quadrigamma 1 times b plus little o of b minus trigamma 1 minus quadrigamma of 1. Oh, I think I forgot this divided by 2 here. Well, much better. Much better this way because you have the Taylor development, so you have to remember that you have 1 by n factorial with the n which is the power of b here. So 1 by 2, and you have here little o of b which is already there, so you have here times b, and up this cancels out, and here you're left with negative a quadrigamma of 1 divided by 2, and you have the rule polygamma for m of 1 equals negative 1 to the m plus 1 power m factorial Riemann zeta of m plus 1, and here m equals 2, so you have here -1, you have 2, and you have the 2 cancels out with the half here, and you have zeta 2 plus 1, which is 3, so you have here negative sign, and you're left with a positive sign, and the b cancels out with this little o of b, which becomes little o of 1, and you're left with 1/8, yeah, it matches, 1/8 Apéry's constant zeta 3. Which is obviously the same result as the one we found previously. So I hope you enjoyed the video. I hope you understood all the developments I made to get this result using the beta stuff and series expansion. Limited development, I mean. If you have any questions, let me know in the comment section. And well, until next time, where we will be solving a very nice integral. I write it that here, the integral from 0 to 1 of the integral from 1 to infinity of t minus 1 to the x power t to the -3 dt dx. Until we meet again, study, learn, and progress. See you next time.